All right, I'm just going to do a little bit of a review here because I feel like it's going to be important in order for you to understand tan. So let's just talk about the unit circle again really quick. We know that sine theta is equal to y, cos theta is equal to x, and tan theta is equal to y over x. Now this one becomes a little bit difficult to see on the unit circle unless you understand what tan is equal to on the unit circle. So let's go ahead and look at the first quadrant and what tan is equal to. So I know that if I'm going to deal with tan of pi over 3, that is equal to y over x. Well, let's clean that mess up a little bit here. We got root 3 over 2, which this line means divide, obviously, 1/2, which is root 3 over 2 times 2 over 1. And these reduce, so we know that tan of pi over 3, the ratio simplifies to root 3. Now let's take a look at pi over 4. Tan is equal to y over x. Which is root 2 over 2 divided by root 2 over 2, which reduces to simply 1, because anything divided by itself is 1. All right, and lastly, I'm going to take a look at tan of pi over 6. That is equal to y over x, which is 1/2, divided by root 3 over 2, which is 1/2 divided by root 3 over 2, which is 1/2 times 2 over root 3. And again, these two simplify, so that's equal to 1 over root 3, or if it's rationalized, it is root 3 over 3. And I think you guys can figure out the quadrantal angles. Now, if we see any of those values, we need to think about, hey, those belong on the unit circle. I only ever figure out quadrant 1, and then using the cast rule, I just reflect them. So I know that this one goes here. So tan is negative here, so this would be negative root 3 over 3. Then I can bring it across here. Tan is positive in quadrant 3, so this is just root 3 over 3. And up here, it's negative root 3 over 3. And then this one I can bring across here, negative root 3. I can bring it down here. It becomes positive root 3, and so forth over here. And I can bring my quarters over, negative 1. Bring it down here. It becomes positive 1, and bring it over here, and it becomes negative 1. So that's one thing I wanted to review with you. The second thing is we're going to be talking about general solution, and I just want to give you a little bit of a heads up before we get into questions. So, general solution, what does that mean? Well, let's link back to what coterminal angles were. So, I'm going to give you an example. I'm going to start in degrees, and I'm going to say, let's say I solved something and I ended up with two angles, one at 30 degrees and one at, let's say, 150 degrees. If I asked you to find the angles coterminal to that, I think you'd be able to do it where you would say, okay, well, theta is equal to 30 degrees, and everything coterminal would be adding a complete rotation. And we would put an n to it, indicating that n has to be an integer because we can only deal with full rotations. And the integers includes the negative numbers as well. And I do the same with 150 degrees. So if I were to write this as a general solution, that would be theta is equal to 30 degrees plus 360 n. And, whoops, I wanted to put those together. 150 plus 360 degrees n being an integer. So that would indicate if we had the solution in one rotation of 30 degrees and 150 degrees, that would be the solution, all angles that appear within one rotation. But the general solution would be all the angles coterminal to those two. Let's just take a quick example in radians so you understand. So let's say I had the same thing, but it was pi over 6 and 5 pi over 6. So let's say I solved an equation, and these are my two solutions within this domain. That would be the solution to that problem. But if it asks for the general solution, and another way they ask for the general solution is they don't give a domain like this. They give it as an element of real numbers, meaning all solutions. What would that look like? Well, think about coterminal. Pi over 6 plus 2 pi n, because we would be adding multiples of 2 pi to get the solutions. And then we would do the same thing with 5 pi over 6 plus 2 pi n being an integer. One thing we have to be careful about, let's say I ended up with one more quick example before we get to the examples. Let's say I ended up with something like pi over 4 as a solution and 5 pi over 4 as a solution. Do you see how those two make an absolute straight line? How do I know that? Is they both have the same reference angle. This we have to treat a little differently. If I were to solve this in the domain between 0 and 2 pi, my answers would be pi over 4 and 5 pi over 4. And what you may think, if I'm asking for the general solution, is, oh, okay, I'm going to do this, add a rotation, and then I'm going to do 5 pi over 4 and add a rotation. That's not mathematically incorrect, but let's take a look. There's a little bit of a cleaner solution than that. What would happen if I added pi to pi over 4? Oh, I get 5 pi over 4. And if I added a pi to 5 pi over 4, I would get the angle coterminal with this one. So we could actually write this solution a little cleaner this way. Because the first angle I get when I add pi to pi over 4 would be this guy. So it's kind of redundant to use it here. All right, now we're going to get to the examples.